Hi everyone. Let's talk about the angle bisector theorem from geometry. The setup is the following. Let's say we have a triangle. And what we're going to do is we're going to label the vertices as A, B, and C. And we're going to be bisecting an angle like this. So there's an equal angle here and here. The idea that we want to pursue is to relate the lengths, the following lengths: AB, AC, let's call this point D, BD, and CD. So this length, this length, this length, and this length. We want to relate them using an equation. At the moment we just don't know whether it's possible, but by the end we'll see that it is doable. But that's the goal that we're starting out with. So let me draw a bigger diagram so it's clear what we're doing. Say we've got A, B, and C, and we've got the angle bisector going to D. What we're going to do now is draw a line that is parallel to AB but goes through C. So we'll call it L. L is parallel to AB and goes through C. And next what we're going to do is that we're going to extend AD until it meets C. And notice that it's definitely going to meet C somewhere, let's say at E, because AB and EC are parallel, or AB and L are parallel. So something in between, like AD, is going to end up intersecting the line L. So we've got this pair of equal angles here, and now we're going to use alternate interior angles. The alternate interior angles that we find are the following. We've got X over here, so by alternate interior angles, X is also here. And we've got O over here, so we've also got O over here by alternate interior angles. So let's write that down in equations. We've got angle BAE is equal to angle AEC, and we've got angle ABC is equal to angle BCE. So this gives us a couple of similar triangles. This one, T1, and this one, T2. So let's write down the similarity that we get. We get that triangle BAD is similar to triangle CED, and that's because this is by AA similarity. Actually, we can say that the angles over here, Y and Y, are equal by vertical angles, but we don't actually need it. Two angles suffice for showing the equality or similarity of triangles. Okay, so we've got a triangle similarity. Let's see where we can go with that in terms of equations. By similarity ratios, we get the following ratios. We get that BA over CE is equal to BD over CD, and that is equal to AD over ED. Now notice that the last one we don't really need, because AD is this the angle bisector itself, and DE is this extension, and we don't really care about those. So let's cross that out. We don't need that. We're going to focus on this equation here. That equation tells us that BA times CD, actually let's write it as AB times CD. AB times CD is equal to CE times BD. So let's look at this. We've got AB and CD. AB is over here. CD is over here. And we've got CE and BD. CE is this and BD is this. So the only thing that's troubling us is the CE. And notice that AC is equal to CE. So let me draw that for you. AC over here is equal to CE, and that's because we have an isosceles triangle with these two equal angles. Angle EAC is equal to angle AEC. So we can substitute in AC for CE. So we get AB times CD is equal to AC times BD, because CE is equal to AC. So that's our angle bisector theorem, this theorem over here. And that corresponds to this triangle up here, but I'll draw it for you one more time down here. We've got A, B, and C, and we've got an angle bisector here, D, and that implies this, even though in the beginning we didn't draw the auxiliary lines and line segments, but by drawing them we were able to deduce this relation. Okay, thank you for watching, and I'll see you next time.